So thank you very much for being here today and for giving me the opportunity to present our startup and our product here. And I would like to begin this presentation citing Christopher Wheeler, who is not here this afternoon, but he said that everyone needs a compiler, and that is really good news for us because we are compiler people, we are producing a compiler. And he also said that some of the major concerns of users are scalability of the software, programmability, programming, and expertise to do the programming to program these new hardware architectures that come to the market. So that's really good news for us because our product and what we do is oriented to that part of the expertise of people. So we are Appentra. This is an spin-off of the University of Coruña in Galicia, only 4 hours driving from here. And we have built and launched to the market for the first time the first commercial version of this product that is called Parallware, which mainly addresses automatic parallelization of sequential codes. So as a startup, it's very important for us to say what is this company, because we know the major players of the market, but we are not aware usually of new startups or new products that are launched to the market and where these companies come from. So Appentra comes from more than 10 years of research and development in compilers, specifically in parallelizing compilers that address the difficult challenge, a long-lasting challenge in the HPC industry. That is, how can we convert sequential code into parallel code that exploits performance of modern architectures? So we did work here mainly oriented to new techniques to discover, to extract parallelism from sequential codes. That was the main challenge that was open at that moment. And after this 10 years, we decided to begin all the road to commercialize this new product and make this research and development prototype a real product that is robust, that is confident, and that can be used in the market. And all that road took almost 2 years. We started 2 years ago, and we have launched the first commercial version only 2 months ago in July. In the meantime, we launched several beta versions. We captured the attention of some beta testers that gave us very valuable feedback, and we mainly got fundings from 30 neotech funds from the Spanish government that are oriented to spin-offs with a very strong technical expertise in their field, and they have to commercialize or launch to the market the really disruptive technologies. So at this moment, Appentra, we have the first commercial version, and we are beginning the phase of achieving the first sales of the product. That's exactly where we are now, and that's one of the reasons why we are here, because we are beginning the prospection and the prospection of the market. So what do we address? It's all well known that computation is the third pillar in modern industry and academia, because we have science and engineering, we have mathematics, we have computer science, and these big clusters, these big supercomputers that we have in many facilities all around the world. And this is called the computational science and engineering field, because we mix all of these elements to finally to write computer programs that solve real problems, approximate the solution, and this is where engineers and scientists need to solve their problems in their fields. On the other hand, we are here, this is organized by BSc and by the HPC Advisory Council, so we are all aware that HPC nowadays is a key enabling technology. It's HPC's competitive advantage. That's something that in this forum is all well known. So the main problem that we have here is that we have programs here running. If we want to solve problems, very large problems or with very high precision, this usually ends up in programs that take very, very long execution times. So in the end, these programs need to be adapted, need to be ported to many types of supercomputers, because all the supercomputers expose a lot of parallelism that can be exploited from the software. So the main problem is that programs, as are usually written in a sequential manner, they all underutilize this parallelism. On the other side, we have very many facilities that help us to port these programs, computational science and engineering programs, to the new architectures and hardware that comes to the field. But really, adapting these programs that have been written for a given architecture is really also like similar to re-engineering the problem in many cases, because we have new standards to program these new tools. We have standards that come with new primitives, with new functionalities, so we have to revisit the programming of our parallel programs. So in the end, adapting programs to this also ever-changing market is really a challenge, and is really very error-prone and very, very long and very time-consuming. To fix the problem, we have made a small experiment, a lean experiment, where we have taken only 3 simple cases that many of you probably know: calculation of P, calculation of fractals using the Mandelbrot algorithm, and a Laplace solver from digital signal processing. These are really small codes of only 10 to less than 1,000 lines of code. And our experiment was done with graduates in computer science that have experience in parallel programming, in particular in OpenMP, because we were targeting the parallelization of these codes using OpenMP, the easiest platform to program. And we gave them a limited amount of time. So we came to these conclusions that for the very simple ones, 100% of the people solve the problem in an optimal way. But when we come to a code that is quite more complex to parallelize, but it has only 67 lines of code, only 5% did optimal parallelization, 47% did cost-effective parallelization, correct, but not optimal in terms of performance, using OpenMP. And what is more remarkable, 48% did a wrong parallelization. The code was translated into parallel code, they could compile it, they could run it, but the results, numerical results, were not correct. So this is something that cannot be, cannot be allowed. So in the end, this is just a small experiment that building CSE HPC applications is challenging even with expertise, very challenging. So our solution comes from a mix of computational science and engineering, HPC, and in the middle one we have a third element that is compiler, and compiler technology to automate the translation of the sequential code into parallel code. So our lemma is just focus on your business. We will take care of parallel programming using the target that we are supporting at that moment. So we are launching to the market a new software tool to address the automatic parallelization of sequential codes. Why is it so challenging? Because if you want to parallelize a code, of course you have to know the computational science and engineering field where you are working. You have to have a deep knowledge of the numerical simulation techniques that you have to use that are appropriate or ad hoc for that field to solve the problem numerically in a correct manner. And when you come to parallelization, the problem is that you also have to take care of computer architecture. The hardware features of the processors are exposed to the programmer. So in the end, you have to take care of some features of the computer architecture of the processor or the memory system, and you also have to take care of this through standard tools such as OpenMP, OpenACC, or many standards that we have in the field. So what we can do, what we address, what we solve with this automatic parallelization tool, what we can do is to decouple the development of parallel applications from the parallel hardware. The compiler, the parallelizing compiler takes care of this with minimal specifications from your side, but you just have to focus on those things that you know how to do. You are an expert on. This is CSE and numerical simulation. So after 2 years of work, we have finally launched Parallware 1.0. That is a parallelizing compiler for sequential codes. As a compiler, it provides simplicity. Ideally, in one click, you should be able to parallelize applications. It has to guarantee correctness. a compiler has to transform their code into an output code, preserving correctness. That is something that the compiler people doesn't always care about. It provides portability. That is, if the OpenMP standard evolves, if we support these evolutions of the OpenMP standard, you just have to recompile your sequential application with the newest version of the tool, so you get portability across different computer architectures. As a parallelizing compiler, we exploit the primary source of performance gain in modern systems, that is, parallelism. And overall, as a whole, for companies and for institutions, organizations, they experience a reduced time to market in wherever is the product of their activity. New products are launched to the market, papers for academic research, wherever. So, in the end, Parallware is an automatic parallelization tool for sequential codes. How does Parallware integrate in your tool chain? If you are building parallel code using OpenMP, that is the first target supported in this version, you are used to using a compiler for OpenMP. You take your source code, you annotate it with OpenMP pragmas, you compile it, and this generates parallel binaries that exploit the power of a multi-core processor, for instance, running multiple threads concurrently. So what we do is, Parallware has been designed to be inserted in toolchain as the first step. Parallware, as input, accepts sequential code, source code, and produces as output. It does not produce binary code. It produces, again, source code that resembles your sequential code, but has, in addition, has been annotated automatically by Parallware with these OpenMP pragmas. So in the end, inserting in your toolchain is a pre-processing step, the first step of all your toolchain. Well, this is a summary. This is not, we are using hundreds of codes internally when we test Parallware, but this is a summary of some representative codes. This TRL5 is the technology readiness level scale to measure the production state of a new product. So we have considered all of these codes from many different disciplines. This is the size of the codes. This is always less than 100 lines of codes. And this is the speed up achieved in this system in the laptop that I have here in my bag. That is a Intel i7 with 8 threads with hyperthreading. So 4 cores, 2 threads per core, activating hyperthreading. So these are really good speed ups for a 4-core machine with hyperthreading activated, automatically in one click. During the last 2 years, we have been conducting the development with these codes, and 9 months ago, we started to work with real codes. These real codes, we can see, consist of thousands of code, of source lines of code, that add input to the compiler, and in one single click are automatically parallelized. And these are, again, the speed ups that we have achieved. For this purpose, as startup, we are focusing on very small market segments at this moment, but we have chosen methods, numerical methods from the computational electromagnetics field, because we saw that computational electromagnetics is a very traversal field that is used in defense, oil and gas for prospections, aerospace industry, mobile designs for the designs of antennas. So we are working now to support, to show that Parallware is able to automatically parallelize numerical source codes written, developed with the most relevant numerical methods, numerical techniques used in this field. So we are using method of moments, that is also known as boundary element method, FDTD, that is a finite difference method in the time domain, and MLFME, that is the multi-level fast multiple method, that is another method used specifically in computational electromagnetics. So in the end, you can see that we can automatically achieve very good speedups. And now we are working in this last case, we will expect to finish in October, that is almost 8,000 of lines of code that are input to the compiler. And it can extract automatically the parallelism available in the code. So I would like to finish my presentation with why using Parallware. The main reason for using Parallware is that it is based on a new technology for extraction of parallelism in sequential codes. These were the main contributions of the 10 years of research that we did in the university, and this is the technology that we have taken to production state as by creating Appentra. It is proven with real codes, not synthetic codes of less than 100 lines of codes, real codes with thousands of lines of codes. We have, as Appentra has exclusiveness in the transfer technology of this technology developed in the University of Coruña, worldwide exclusiveness. And in the end, the main goal of Parallware for OpenMP targets, for multi-core systems, is to extract the coarser-grain parallelism available in the code. That is what will provide you on a node of a cluster running a multi-core processor the highest performance, reducing the communication overhead or the parallelization overhead in general. Users that tested reported us that they were really impressed by the technology. Of course, by the product, because it is automatically parallelized, it's something new in the market. But they tested the technology, they were aware of traditional technologies for discovering parallelism, and they were really impressed by the power of our technology. Why using Parallware? Okay, we have tested that it works. It does what we claim, with codes from computational hydraulics, codes from oil and gas from seismic prospection, codes from computational electromagnetics. And for you to understand why it works and why we claim that it will work for other computational science engineering fields, is because all of these fields, in the end, in the numerical techniques that they use, numerical methods that they use, they are using finite elements, finite volumes, finite differences, smooth particle hydrodynamics. They are using methods, numerical methods that are used in many fields. So we are showing that Parallware works and is able to parallelize automatically numerical codes written with these numerical schemes, these numerical codes. So if you apply it to another field, the formulas will change, but the structure of the program, from the point of view of extracting parallelism, will be similar to other fields, because it in the end depends on the type of method that you are using. As I said before, straightforward tool integration is just a pre-processing step. Input, source code, sequential, output, source code, parallel annotated with OpenMP. And I will not go into the details of many features that Parallware may support or not support, because I don't think that is something that we should discuss here, because we can discuss it in detail for each example application, each method. But what I will try to present here is what we think as a startup company that will be the roadmap for this product. So we have the main types of architectures that we have in the market. This is a processor, a core that supports SIMD instructions in the instruction set architecture, typically SSE, AVX. These are multi-core processors. So in the end, we have big clusters that have nodes, and these nodes have multi-core processors. These multi-core processors are usually programmed with different tools. We classify these tools according to the productivity level or degree of automation. So in the manual level, we can make parallel programs for multi-cores using POSIX standard. But we usually use in scientific and industrial domains a semi-automatic tool based on the OpenMP standard that in the end takes care of all the burden of handling and using this POSIX library to communicate threads within the processor. So Parallware for multi-cores, this is the target for version 1.0, supports the OpenMP standard. Version 3 to extract the parallelism to feed 4, 8, 16 cores per processor. And we will always support as output open standards so that we can preserve portability of our clients. For many cores, either GPUs or Xeon-Phi accelerators, they are usually programmed in the manual level with CUDA or OpenCL. in the semi-automatic level, the last version of OpenMP has new features to support the programming of these accelerators within the same node of a cluster. And there is another standard, apart from this extension of OpenMP4, that is OpenACC, that usually, in the end, they both support the same functionalities. That is, what part of the code do I offload to the accelerator, GPU or CMFI, or AMD APU, and what amount of data and exactly what data from the main memory of the CPU do I have to offload to transfer to the accelerator, for instance in GPUs. So both standards take care of this. And 1 year ago we started the company developing the technology for extraction of parallelism, and we plan to support both OpenMP3 and OpenACC. Finally, because we are a startup, we decided to launch the first commercial version with OpenMP. But 1 year ago, we built a prototype, a functional version of PARALWAR internally in our research and development department that was able to automatically generate code for a GPU using the OpenACC standard. We were able to automatically decide what parts of the array had to be offloaded to the GPU, map this data to the memory of the GPU, and decide what segment of code would be executed in parallel in the GPU. And this worked also 1 year ago. But in the first commercial version, as I repeat, was launched with OpenMP for multicores, for simplicity of the development. And finally, when we talk to users, they say, okay, but can you support MPI? Can you automatically generate code using MPI to automatically generate code for clusters? So our answer was we think that we can. And the reason was that the technology for extraction of parallelism gives us the whole picture of what is happening in the whole application. When you try to parallelize code, if you have experience with OpenMP or OpenACC, you have the whole application, you focus on the hotspots, on the bottlenecks, and you can incrementally decide how to parallelize this. In MPI, you cannot do that. You have to take the whole picture, take a look at the data structures that you are using, how they are traversed, how they are computed. So in the end, you need the whole picture of what the computations look like, what the data structures look like to address the parallelization. So we know that our technology gives us the whole picture of the program, and we decided to make, as we did 1 year ago with OpenACC, to build the first experimental version of PARALWAR, internal version, that is able to automatically generate MPI code for a simple set of applications. We finished this internal development in July, 2 months ago, and it worked. So when we are asked, OpenMP standard for clusters, can you support it? The answer is, we have the technology to do it. But for that product to come into the market, it is quite much more complex from the point of view of extraction of parallelism. That is OpenACC, OpenMP version 4, or that is OpenMP for multicores. So it will take time for us as a startup company to make all the development to be able to support this for real applications. But we can do it because we have the technology to do that. And we have a prototype to show it. So if you want to try, please just request a free trial. Just contact us and you can try the tool. And also we have a full version that we can provide you a license for 30 days, for instance, if you want to evaluate it. And we can work with you to evaluate what are the current limitations of the technology. And including our development roadmap, we can tell you if we plan to support specific features of your applications in the near future, in the medium term, or in the long term. So that is, we think that this is important, that for the full version to work with the potential user, because this is the first version of PARALWAR. Okay, but you have a free trial to try it. Thanks, and that's all I wanted to tell you today. Any questions?
Any questions for Manuel? Will you be showing this at Supercomputing in the United States conference? ESC?
In November.
Yeah. Are you coming?
We had not planned to be in November there. We finished the first commercial version in July, and we started to make our prospection of the market and what events should we attend in the short term. We decided to come here, and we plan to be in Hamburg probably in 2015, within 9 months.
Frankfurt, yeah, Frankfurt.
Frankfurt, sorry.
Very good.
We plan to be there in 7 months.
Okay.
It was not very timely for us to be in the US in 1 month.
Yeah.
We would like to be there, but it was not possible.
Any other questions? Yes.
Why not addressing the GPU target?
Okay, I have not a slide here. These are technical reasons. To automatically generate code for multi-core processors, shared memory, the complexity of the compile time analysis that you have to address is simpler because you don't have to take care of range analysis to know what exact regions of, for instance, an array you have to map or you have to transfer or offload to the GPU. So we know that we can detect what part of the code can be offloaded to the GPU. The problem is that the technology is still maturing to determine exactly what parts of the array have to be offloaded to the GPU. That requires the implementation of some kinds of analysis that we are already doing in Parallware, but they are not still in, let's say, in production state to launch a commercial version that is reliable and that is robust to generate code for that part. But we can extract the parallelism even for GPUs or for many cores. We have not automated the generation of the code. That's the part of the development that we are still taking care of. We don't know how to do it. If we are a startup, we have to decide our priorities and launch something to the market to make the... Okay.
Any other? Okay, thank you.
Thank you very much.